Welcome everybody to this presentation. I'm going to be presenting this paper on H-integral Sombor indices, theory and chemical applications. This is a work with Professor Sedil Molina and José Rodríguez and José Sigarreta from Universidad Autónoma de Guerrero and Universidad Carlos III de Madrid. Before starting, let me introduce you some concepts that are going to make the presentation more easy to follow. First, a topological index is a graph theoretic invariant which reflects the structural features of a molecular graph. What do I mean by a molecular graph? A molecular graph is simply a graph representing carbon atom skeleton of an organic molecule, where the vertices represent non-hydrogen atoms and its edges represent covalent bond between the corresponding atoms. In case someone doesn't know, a graph is simply a structure that is used to model pair-wise relationships between objects and is composed by two things: the vertices and the edges. In this case, the vertices are represented by these atoms and the edges are represented by covalent bonds between atoms. Topological indices are useful since they summarize some structural properties of molecules into single numerical values. In particular, the vertex-degree-based topological indices play an important role in chemical graph theory. Our interest in this paper is the vertex-degree-based topological index called Sombor index, which has been recently introduced by Professor Evan Gutman, and the regularity integral Sombor indices that I'm going to be defining in a moment. Let me talk about a very simple example of why these topological indices are useful. Although only about 1,000 benthanoate hydrocarbons are known, the number of possible benthanoate hydrocarbons is very huge. And therefore, to model the physicochemical properties is very important in order to predict properties of some potential unknown species. Now I'm going to be talking about the Sombor index, and I'm going to introduce some notation. Through this work, G is going to denote a finite simple connected graph. This is a graph where the vertices are finite, and connected means that there is not a single vertex that is not connected to any other graph, where B is going to denote the number of vertex, and E is going to denote the number of edges. Then we have the degree of a vertex that we are going to denote by the letter D. So if there is an edge from vertex U to vertex B, we indicate this by UB or VU. With this said, we can go to define the Sombor index, which is as follows. It's simply the sum over all the edges connecting to vertices U and B of what? The square root of the degree of vertex U to the power of 2 plus the degree of vertex B to the power of 2. So each edge UB is represented by a point xy in the two-dimensional metric space, such that its distance to the origin is precisely the degree of the radius of UV. So summing over all the edges connecting these two vertices, U and B, we get this Sombor index. So in this paper, basically we continue the study of topological indices from a geometrical point of view. We propose and study the H-integral Sombor indices. We generalize the first and second irregularity Sombor indices that we presented in a different paper, but I'm going to be reminding a bit in this presentation. And in particular, we present the new inequalities that refine the existing bound on topological indices, enhancing their predictive accuracy and applicability in chemical graph theory. We also study the application of H-integral Sombor indices in modeling the entropy of property of octane isomers. Okay. Now I'm going to be defining some objects that are going to be helpful to follow the presentation. We are going to say that, let me start reminding a bit what are the first and second irregularities Sombor indices, and then we are going to generalize these indices, okay? We say that a set of functions G is a regularity admissible if its function G is a rectifiable function and the following property is satisfied. For each positive integers, A and B, there exists a unique alpha such that G evaluated at A is equal to B and G evaluated at B is equal to A. So we define the two following objects, this H1, which is simply the integral in the interval of the minimum value between A and B and the maximum value between A and B, of what? The square root of 1 plus G prime to the power of 2, which is simply the length of the graph G. The second object, H2, is going to be, again, the integral in the interval between the minimum value of A and B and the maximum value between A and B of the function G, which is simply the area under the graph of G. Okay, so to compute the first and second irregularity Sombor indices, we need these two objects. And we're going to be defining the first and second irregularity Sombor indices as follows. Simply, the first irregularity Sombor index is the sum over all the edges connecting the two vertices U and B of what this first object that we have defined, this h1, which is the length of the graph. And the second irregularity Sombor index is simply the sum over all the edges connecting U and B of the second object, which is the area under the graph, this H2 that we have defined, okay? So now with this in mind, we are gonna generalize these two indices, okay? And we're gonna do it in the following way. So given a function h, which is bounded on each compact interval, we say that a set of functions f is h-admissible if its function is absolutely continuous, is an absolutely continuous function satisfying the following property. That for each positive integers, a and b, such that a is bigger or equal than b, there exists a unit alpha such that h evaluated at a is equal to h evaluated at b, okay? Which is a very similar property as the one that we had here, okay, for the first and second irregularities on board index, okay. So now we can define two objects that are very similar as before. This f object, this f1 and f2, which is simply the same thing as before, but now the integral is going to be defined instead of between the minimum value of a and b and the maximum value between a and b, it's going to be defined between 0 and the function h evaluated at a. Why? Because a is bigger or equal than b. Of the same thing as before, the square root of 1 plus f prime to the power of 2. And the second object is going to be the same, the integral between 0 and the function h evaluated at a of the function f, okay? And we are going to build what we call the first and second h integrals on board indices in the same way as before. We are going to be summing over all the edges connecting the two vertices u and b of what this object that we have built now, this f1, and the second h integrals on board indices is going to be again the sum over all the edges connecting u and b of the second object f2 that we have built. Note that for h equal to x, we have the first and second regularities on board indices, okay? We can also generalize some other important indices, as are the first and second Zagreb indices and the Sombor index. Let's say that for any graph G, we can define the following thing, this HM1, which is simply the sum over all the edges connecting two vertices U and B of what the function H evaluated at the degree of U plus the function H evaluated at the degree of B, which is the first Zagreb index, and the second Zagreb index, this HM2, is going to be the sum of over the same thing of what H evaluated at the degree of U times H evaluated at the degree of B. And also we can generalize the Sombor index, this H Sombor index, which is the same as the Sombor index that we have defined before, but instead of having the degree of u to the power of 2, we have h evaluated at degree of u to the power of 2, and h of the degree of b to the power of 2. Note again that if h is equal to x, then we have what we know as the first and second Zagreb index and the Sombor index. With all these definitions in mind, we can go to the theoretical results, okay? And then I'm going to be talking about the empirical result that we obtained. In the theoretical results, simply I'm going to be showing a few of them because we have many and I don't want to make this presentation extremely long. But there are two types of results. I'm going to be talking about some results that link the relationship between these H integral Sombor indices and some of these other important indices that I have talked as the first and second Zagreb index and the Sombor index. And then we are going to be refining some of the bounds on these existing topological indices, okay? So let's start. Let's say that f is an h admissible set of functions such that f evaluated at 0 is equal to 0. Then we have this result that the first h integral Sombor index, f1, is going to be bigger or equal than the h Sombor index for every graph G. We also have this other result that, again, if f is an h-admissible set of functions, that f evaluated at 0 is equal to 0, and f is a non-decreasing function for each alpha, then we have that the first irregularity h integral Sombor index, is smaller or equal than the h the first Zagreb index for every graph G. Similarly, we have some result for the second integral Sombor index. Let's say that if G is a graph and S is bigger or equal than 0, then we have that the second irregularity integral Sombor index is going to be equal to 1 over S plus 1 of times the H second Zagreb index for every graph. Now let me talk about some of the bounds that we have refined for the some of the indices, some of the topological indices. Let f be an h-admissible set of functions such that f prime is an absolutely continuous function for any alpha, and let a and b be a natural number with a bigger or equal than b. Then we have that the first object that we use for computing the first h integral Sombor index is going to be bigger or equal than this object here. It's a bit ugly, but the important thing is that we can compute it. And also, we have the following thing that, again, this first object that we compute to compute the first h integral Sombor index is going to be smaller or equal than, again, the square root of this object here. So this is one of the bounds that we obtain. Similarly, now let G be a graph with m edges with a maximum degree capital delta and a minimum degree small delta, and define capital omega as the supremum of h evaluated at the degrees of the degrees of the vertices, and a small omega as the infimum of h evaluated at the degrees of the vertices, okay? And let G be an h admissible set of function with this particular functional form, and with s different from zero, and then we have that the following facts hold. We have that the first integral Sombor index, h integral Sombor index, is going to be smaller or equal than this object here. Second, we have that this is positive. Then we have that, again, the first h integral Sombor index is going to be bigger or equal than this object here. And we also, sorry, and also we have that this is smaller than zero. Then what we have is that the first integral h integral Sombor index is going to be bigger or equal than this other object here, okay? Similarly, we have that, again, if G, let G be a graph with m edges and a maximum degree capital delta and a minimum degree small delta, and again, define the supremum and the infimum in the same way with these letters capital omega and small omega. And let f be an h-admissible set of functions, now with this particular functional form, then the following facts will hold. If s is bigger than 1/2, then we have that this inequality holds, that for the first h integral Sombor index is going to be smaller or equal than this object here. And if s is bigger than 2 or equal, then we have this other inequality here, then that is that the first irregularity the first h integral Sombor index is going to be bigger or equal than, again, this object here, that even if they look ugly, they are easy to compute. Okay. So now we can go to some of the empirical results in which we are going to investigate the capability of the first and second h integral Sombor indices to model the entropy of octane isomers. Our approach will utilize parameterized families for both the h-admissible set of functions f and the degree of transformation of the h function. We introduce two positive parameters, the p parameter, which primarily tunes the shape of the functions f, while q controls the degree of transformation of the function h. We are going to have three different families of functions. The first family is going to be denoted as this k type of function, which is simply equal to alpha times p over p plus x, combined with this h function, which is going to be 1 plus e to the power of minus qx. This uses a rational kernel function, family k, and an exponential decay transformation for the functions h. The second family that we're going to denote by L, the type of functions L, is going to be equal to alpha times 1 over p plus e plus e to the power of minus px, combined with this type of h function, q times x. This is going to pair an exponential decay kernel family with a linear degree scaling for h. And finally, the third family, which we are going to denote by the letter t, the functions t, is simply going to be alpha times the tangent of p times x, combined with an h type of function, which is going to be 1 plus x plus e to the power of minus qx. This employs an hyperbolic tangent kernel for the family t, with the same exponential h functions for as in the family one type of functions. Okay. So now let me go to some of the results here. What you are seeing in this color map is in panel A. We are showing the correlation between the first H integral Sombor index and the entropy of octane isomers for the first family of functions that we have defined. And we have this correlation evaluated at different values of Q and P. And in panel B, we have the same thing, but for the second H integral Sombor index. And you can see that we obtain a maximum value of correlation of 0.96 and for the first type of family, and again 0.96 for the second H integral Sombor index. For the second family of functions, we have the same thing here. Okay, we evaluate in the panel A for the first H integral Sombor index and the panel B for the second H integral Sombor index. And we evaluated the correlation with the entropy of octane isomers for different values of P and Q. And again, you can see the different type of values that we get for the correlation and this different combination of P and Q. And finally, we have the same thing for the third family of functions for in panel A for the first H integral Sombor index and in panel B for the second H integral Sombor index. And finally, we are going to run a regression on what the entropy of octane isomers, and we are going to run the regression on the first and second H integral Sombor indices and a constant. Okay, so we are going to parameterize this in the using the values of P and Q that maximizes the correlation for each type of functions and for each H integral Sombor indices. Okay, and this is the results that we get. C1 is going to be the slope and C2 is going to be the intercept in the regression. Okay. And yeah, this is basically all that I wanted to talk about in the in this presentation of this paper. I hope that you enjoy the presentation and thank you for listening.